When you are starting in modern IT, so that is not Network Plus, A Plus, and CCNA and all that. I'm talking about cloud, DevOps, machine learning, MLOps, data science, AI, and all that. You need to have a foundation of IT. You need to understand the cloud, because most probably if you are in any of these professions or even in cybersecurity or development, you are going to use some sort of cloud, if not multiple clouds. So understanding what is cloud computing and why did we get into cloud computing and why it is attractive is very important. Also, if you are going to work on automation and you are going to work in DevOps or MLOps, you need to understand why do we need it? Why do we need automation in that part? And that takes us to understanding what's agile and what was done before that, and why do we need DevOps and why do we need MLOps and so on. Understanding DevOps definitely is going to give you the importance of MLOps as well, machine learning ops, and then AI ops, and there's a lot of XXX ops in the field right now. So these are two important parts anyone in IT should know and should understand, at least at a high level. We're not going to dive deep into this course. It's a crash course to explain what cloud is and why did we get into it and why it's going to remain, and also to explain what is DevOps and what was happening before that and why it is important. Then understanding networking fundamentals, not CCNA, not Network Plus. Understanding fundamentals of networking is crucial in order to get into any of these fields, especially if you are going to be on the engineering side. Even if you are a developer and you would like to establish presence in a cloud and you would like to deploy your application, whether it is on virtual machines or containers or orchestrated user Kubernetes or OpenShift, you will use the cloud, especially if you are going to work for small companies, startups, or companies that have migrated to the cloud. So understanding networking and what are IP addresses, why do we need them? If you are given a block of IP addresses, how can you divide it based on requirements? What is a router or a router, and why do routers exist? What do they do? How can they connect different networks together? What's a local area network and what's a wide area network? What's a routing table or a forwarding database in a router? All of that are important terms that you need to understand, and they are going to be explained in a crash course, which is this video, and hopefully that will be beneficial. And of course, there will be a more detailed ones that will be coming up, and we are currently working on a more detailed foundation course that will make people avoid going and wasting time on A Plus and Network Plus and CCNA and CCNP and the Cisco route, which is old IT. All right, so hopefully that is going to be a beneficial course for you. Please consider subscribing to the channel and activate the notification so you will know about videos like that if these are important to you. And if you benefit from the course, please consider giving us a thumbs up, a like, and share in order to benefit more people. So stay with me till the end on this sweet, concise, and very beneficial cloud, DevOps, and TCP/IP and networking fundamentals crash course. Hi everyone, welcome back. In this course, we are going to cover the IT, cloud, TCP/IP, and DevOps fundamentals. My name is Isa Abu Sharif, and I'm going to be your instructor for this course. Let's start with IT fundamentals. Let's talk about compute devices and their common components. Compute devices encompasses a lot of devices that we use on a daily basis, and that includes laptops, iPads, iPhones, mobile phones, servers, anything that has to do with processing that we use, which includes apps that we use on a daily basis. And although each one of them is used for a different use case, but they have a lot of things in common. And that's what we are trying to focus on in this lecture. So common components for computing devices include the CPU, the central processing unit. The central processing unit is considered like the brain, the main muscle in the computing device. And this is where all the instructions, all the input and output operations, data exchange, processing happens, and that is existing in every single device. And some devices, they could be powerful enough where they could have more than one CPU inside them. Then we have the RAM, or the random access memory. This is where when you run one of your applications, it runs in the RAM. So for example, you are running Microsoft Word or PowerPoint, or you are using Google Chrome, or using an email client, Outlook, or whatever it is. Then when that file or that application starts, it runs in the random access memory or the RAM. Then we have the storage. Now I'm working on a PowerPoint file or a Microsoft doc file or an Excel sheet, or I'm working on any type of data, and now I need to save that file. Why do I save it? Because if the battery in the device runs out, maybe I'll lose the data. So I want to make sure that I save it so it will be there. Even if I switch off the device and I start it after 1 week or 2 weeks, I still have access to the data or the file that I was working on. And that's why we need a storage or a hard disk drive, or sometimes, depending on the technology, it's called solid state drive as well, which are faster ones. Then we have the network cards or interfaces. When we connect at home and we are on Wi-Fi, how is that happening? How is that exchange happening between my phone and the Wi-Fi network at home? There is a built-in Wi-Fi adapter that facilitates that in your phone and also in the router at home. Similarly, if we have a server connected in a network, then that server needs to be cabled into the network. It needs to be connected into the network. How? There is a network interface card. So the type of connectivity can be cabled, or can be physical, or can be Wi-Fi, wireless. Then we have the monitors. I mean, we look at the phone and then we can see a lot of things. This is your monitor, laptop. If you have a desktop at home and then you have a bigger screen, these are all monitors. Even the TV at home, it has the CPU, it has the input output, and it has the interface for the network, either Wi-Fi or wired, and it does have a monitor because its function is to display movies and shows and stuff like that for you. Then we have the graphic CPU or the GCPU. This is in case if we have a device that does a lot of rendering videos and processing videos and editing videos and movies and stuff like that, then it's better to have a dedicated card called the GCPU, because it accelerates the processing of graphics or graphic related content. So definitely there are more components than this, but these are the important ones that we need to focus on to serve the purpose of what we are trying to explain in this series of lectures for the ITF or the IT fundamentals. All right, now let's talk about servers. What is a server and what do we mean by a physical server? So when you listen to that term or you hear it, you know what we are talking about. So a server basically is where we put the applications. It's a muscle computing device that can process much faster. It can serve multiple requests from many clients at the same time without sweating and losing breath. That's basically what the server is. So can I use my laptop as a server? Yeah, maybe. If the users that are going to use it will be 5 at a time or 6 or 10 at a time, maybe you can get away with using a laptop or an iPad or something and then putting some application users can log into. But if you're talking about Amazon.com, eBay.com, CNN.com, I mean these big websites, then we cannot get away with a weak or a mini computing device. Many in terms of muscles, in terms of CPU, in terms of power and all that. So the server basically is a powerful computing device that could have multiple CPUs. It will have a good sized memory and it will have one or more disk drives to store data. Of course, it needs a bigger space and a bigger size to do that. It can have one or more network interfaces and it can have one or more GCPUs. So same components in principle, but now the quantities or the sizing of these components is different and higher. To work with the server, then you have these components we discussed, but also you need to install an operating system in the most part or in the most cases. You have an operating system, Windows or Linux or Mac OS, and then you can start application on top of that. So the server itself is a piece of hardware that you need some software on it to run. So the software is your operating system and it can be your applications and so on. And of course, when it comes to a muscle server or a powerful server, then we are talking about something or a device that can serve hundreds or thousands or tens of thousands or maybe more of clients or users that will be accessing that game or that application on the server. When we talk about the CPU, the measuring unit for the CPU, or how we specify whether that a CPU is powerful or not, is in terms of gigahertz. And of course, the generation as well. I mean, you have generation 9 and you have an Intel or AMD. You have different types of CPU manufacturers and also different series or generation within each one. The memory and storage, they are measured in gigabytes or gigabytes. And the network interface card speed is measured in megabits per second or gigabits per second. Now let's cover an important concept, which is virtualization. So what we discussed in the previous lecture was physical servers. Now we are talking about virtualization. Is there a way, if my server and the applications on it are underutilizing its resources, is there a way I can have multiple virtual servers on top of the physical server? Why would you do that? Better use of resources. And maybe I need to run Linux server and Windows server on the same physical one without having to acquire a new one. So what we discussed so far is when we have a physical server, then we'll have the components, which are called the hardware, and then we have the operating system and applications, which are called the software. Now, what if I need to run an application that requires Linux operating system, not Windows, and I need to run it on the same server? So in that case, we have to go for what we call virtualization. So virtualization is, in the simple terms, dividing your server virtually, logically, into multiple servers. Each one of them is going to be separate and isolated from the others. And each one of them can have its own guest operating system or operating system on its own. And it can have its own applications also on top of that operating system. So we might have a virtualized servers where we have a Red Hat Linux virtual machine or virtual server next to a Windows virtual server next to an Ubuntu Linux operating system server. And each one of them will have its own applications installed on top of that. Okay, how can I manage to do that? How can this server access the outside world? How can they get to the storage? How can they get to the outside in terms of Wi-Fi or in terms of connection to the network and then to the internet, for example? How can the clients from the outside access a specific server and not the others? This is through what we call a hypervisor. So we have a software layer on the server that will be installed, and that software layer is going to be the facilitator of providing each virtual server its own requirements of memory, disk, CPU, GCPU, network interfaces, and so on. And at the same time, it will know if the traffic is coming from the outside to this server, how to communicate with that server, and how to get the response back to the client. Similarly with the other servers. So the hypervisor is an emulation layer that will make every one of these virtual machines feel and be convinced that it has whatever it needs from disk and memory and CPU and all that, so the application and operating system can be installed successfully. So virtualization enables us to run more than one virtual system at multiple operating systems and complete isolation on the same physical server. Okay? And the hypervisor, as we mentioned, it used the virtual instances of the hardware to create virtual machines. So basically what we are doing is we are sharing the hardware on the physical server logically among the different virtual machines that we have. And on a server, we can have 10, 20, 50, 60 virtual machines working, functioning, and each one of them will be happy, performing whatever it is required or it is supposed to do without any issues. Okay. Now, how many can I put? Is there a guideline? It all depends on how strong and powerful the original server is, because now you are sharing its own hardware and all that. So you don't want them all to oversubscribe and demand more than what the server has at all the time in terms of memory and storage and CPU and all that. then you will have a problem, or that means you have overutilized or have abused the capacity of virtualization that you can have on this server. Now, when I have a virtual machine, the physical server was easy to remove from one location because I can touch it and feel it and then port it or lift it into another location. I can do that. But what about the virtual machines? When you want to have a virtual machine moved from one place to the other, or maybe you just need to have a backup of that virtual machine just in case, because that is software. If a problem happens, then you can restore your virtual machine and the services on top of it, or the applications on top of it. Then you can have a file that will be the backup of your complete virtual machine. So that means if you want to install it on a different server, all you need to do is to take that file and then install it on the other one, on the other server that has the same hypervisor or a compatible hypervisor. Same thing for the Windows, same thing for the other Linux. So you can always have a snapshot or a backup, and that will be what you need to restore it on a different server if you want. So the virtualization components now for the virtual machines, each one will have its own operating system, its own applications, but also each one of them will be told by the hypervisor that you have this much of CPUs in a virtual format. So basically you are sharing this much of the CPUs from the physical server, and you are sharing, or you are being allocated this much of memory, virtual memory, from the original memory. And same thing for the disk, and same thing for the network interfaces. All right, so now let's get into a new topic, which is web applications. We're going to hear that term a lot, and especially when we learn the cloud and we get into architectures that involve a lot of services. And now the fine line between the different services and domains is kind of melting, and now we have overlap. So you could be a solutions architect, you'll be sitting with developers, and you'll be sitting with people that have to do with application architectures and application developers and ops and admin and stuff like that. So you need to have the lingo, or you need to speak the language of all these people. So it's good to have a baseline or a foundation to understand what an application, when it is signified or when it is designated as a web application, mean. So we talk about client-server applications. That means it's a client, like the browser. It could be Google Chrome, and we are accessing a website or an e-commerce website. So that's a client-server communication. But when we say that's a web client and a web server or a web application, that means they are accessible through the internet, which means that the user is going to send in the request, and then a response will come, and both of them are going to fly, or they're going to be transmitted over the internet, transported over the internet. Now let's introduce data centers. Now we talked about servers, and we said that the physical servers are installed on top of them applications, and there could be also virtualization and virtual servers and all that. Where do we place it physically? That server that has 10 virtual machines, do I put it in my bedroom in a closet, under my desk? Do I put it in the garage? Or do I have to have a designated space that has been prepared to host these applications and this hardware, the servers? And this is what we call data centers. So data centers, they could be as small as few meters by few meters space that is air conditioned, powered and everything, or they could be as huge as maybe thousands of square feet in different floors, even in a building, or it can be completely a separate building that is used for the data center. So it could be as small as one of these cabinets, and we call it tracks, or it could be aisles and aisles and aisles of servers, and then a raised floor where the cooling and stuff like that can run underneath, and then a false ceiling where the cables also and cable trays can flow on top. So a data center is where we host our servers and our applications. So in general, a data center is a considerable space size that is air conditioned, powered, secured, manned to ensure continuous operation. So where do our servers fit? The physical servers, and we call them rack mountable servers because they can be installed in racks or cabinets. The cabinets, they have a back side and they have a front side. Front side shows you the nice flickering green and yellow and red and orange, depending on the situation, LEDs. or lights. And the back is where we connect all the cabling. And that's how we hook the different devices into the network and into the storage network and stuff like that. And then we start building rows of racks that have devices inside them. And then we have to have aisles between the rows so we can access the front side and the back side. And that's how we establish the data center. Now let's dive into cloud computing. Since we discussed and we defined at a high level what is a data center, now let's look at cloud computing and why it is changing the game of IT right now, or the IT game changer. So data centers are called also interchangeably on-premises locations or headquarters or whatever it is. So these are the customer side or the customer space or the customer real estate basically. Okay, so how does that compare to the cloud? What's the problem with the on-premises data centers that is tempting a lot of customers to move to the cloud? What is the solution that the cloud provides for an issue or a limitation we have with the data center? And that is what we are trying to find out right now. Okay, so let's look at the on-premises data center. It's basically your responsibility, Mr. Customer, to do everything. The whole thing or the entire 9 yards are your problem and your issue to fix. What do we mean by my problem? I mean that you as the customer are responsible for selecting the location or maybe leasing the data center space, then designing either on your own with your teams, or you'll have a consultant that will come over and find the requirements and start designing the data center, to the power, high voltage and low voltage and whatever that will feed into the data center. You need power generators or diesel generators in case of there's an outage of power, then that will kick in and keep the data center up and running. Costing all of that, paying for it, building it, operating it, enhancing or optimizing it, and also doing any upgrades or refresh cycles. Every 4 or 5 years, you need to change the hardware when it becomes obsolete or out of performance requirements, or it's a new model that have more power or more features that you need for your infrastructure. So basically you are on a continuous base, you are spending on the data center upfront and an ongoing base as well. Okay, so that's called a CapEx model, a capital expenditure model. So you want to buy a server, pay for it, and then order it, so it will be shipped after some time, it will come to you. You want to expand the data center, you want to refresh, you need to add a new feature, you need to add physical security, you need to change the cameras, you need to do this, that, whatever it is, pay for it, Mr. Customer, and we'll be gladly supporting you to achieve that. And in that case, the customer is responsible for everything from the network to the storage, to the hardware, to the virtualization, to the operating systems, to any message brokers or middleware between the application components, and then to the runtime, whether you are running Java, or you're running Go, or you're running React, whatever you are running, then you need a runtime to run these programs using which you have written your applications. And then to the data itself and maintaining the data and backups and all that. And then we have the application itself to run and use that. So everything, the full thing is your responsibility, and you have to pay in most cases upfront for all these expenses. And don't underestimate what a real data center, like a sizable data center, would cost from a build perspective and from an ongoing operation and staffing and all that perspective. It's a lot of money. We are talking about millions, if not tens of millions every year. So let's look at the cloud, and how would the cloud change that? How would the cloud take away from these responsibilities? How would also the cloud change the cost model or the financial overhead model of the data center? So in cloud computing, everything the customer needs is pre-built. So the cloud provider has taken your data center and has built it, and whether it is dedicated for you or for public use so anyone can use it, then why do we would say that it is cloud computing or computing in the cloud? Because I as a customer don't care and don't know where the data center is. I don't know anything about the details, how big, how small, how it is air conditioned, which brand of air conditioning, what physical cameras, how many people are running it. I don't care about all of that, as long as I can use it. If we want to have an analogy for that, think about the power grid. The power company or the utility company that you are subscribed to and you're paying bills every month, do you know where they are? Do you know how they generate the power? Is it using coal, or is it a nuclear plant, or is it with waterfalls, with solar energy? You don't know, and you don't care. As long as they're providing you the power that you need at a reasonable price, if you have a choice to go to another one, or maybe it's a monopoly, so you will have to have and pay for what you use, and that's it. So it's a utility bill that comes at the end of each month, and then you have to pay it. Otherwise, if you don't pay for maybe 1 or 2 times, then they will just cut it, and then you have no power at your home and you cannot survive. You cannot run your computers, charge your phones, and all that. So cloud computing follows that utility principle or model when it comes to paying for what you use. And if you don't use it, you don't pay for it. Exactly like if you travel and then you switch off all your devices and all your lights and all that, then you haven't consumed anything, or maybe a little bit only for some cameras or stuff like that, then that's what you pay for. So it's a pay-as-you-go model as opposed to the CapEx model, and that's why we call it an OpEx model, an operational expenditure model. Whether you use databases or servers or security or storage or whatever you use, there you have monitoring and billing that will find exactly what you have used, and then you will be billed for that. And that's why it's tempting, that's why it's attractive, and the most important part, not only the cost, but the fact it's pre-built. So I'm using something that is built. I don't have to order servers. I don't have to connect cables. I don't have to bring or build a network. I don't have to bring storage devices. It's all there. And there is an easy portal that also makes the use of that very, very friendly. So you can learn quickly how to use it and start using it. You need to use a server, then you can turn it on, you define the specifics, then it's on in 2 minutes, 3 minutes, you use it for 1 or 2 days, and then you switch it off. That's how it goes. And that's all what you need to do. Okay, so we are here at the perfect time, and it is time to learn the cloud, and I think it's going to be here for years and years to come because of the OpEx model and because of the agility and speed and the fact that it's a utility bill at the end of the month. And now we need to focus on what are the cloud types. We'll hear these terms frequently: private cloud, public cloud, hybrid cloud. So we need to find out what this is all about. Before we do that, let's take a step back and ensure that we understand the difference between a data center and a cloud. So is a data center equivalent to a cloud? And the answer is no. The cloud has one or more data centers, but it has more than just a data center. The cloud is about the portal, it's about the ease of use, and it's about a service catalog that shows or presents the services the cloud provides to the customers. So I don't have to know the complexity of the underlying infrastructure, but I should be able, through a portal, to do some clicks here and there and then have the service that I want to start and use available. So the cloud is actually a data center or a collection of data centers plus what we call the automation and orchestration. So basically, the portal is one part of it, but also the integration between the network and storage and security and software and licensing and all these features the cloud provides. This is what the automation and orchestration is. This is when you click multiple clicks and you don't know what's the underlying infrastructure, magic happens, and this number of clicks are going to invoke a lot of things under the hood, and then your services are going to be provided. So when we combine this with that, then we get what we call the cloud. Now let's look at the cloud types. If you have the automation and orchestration on a data center that you own, you Mr. Customer own, or multiple data centers that you own, and it is solely for the use of your company or your enterprise, so in this case, the resources are for private use, and maybe the data is confidential and it only belongs to your company, and that's why you built a private cloud, but it still has the ease of use for the customers. However, all the customers are your employees and your clients. Or it could be a public cloud like AWS, Azure, Google, IBM, Alibaba. All these clouds are built for public use, and they are shared and they are multi-tenanted, which means customers from all different sorts and all different places, they could be using the same cloud for their own use. The predominant way of connecting to these public clouds is the internet, and it is best suited for less confidential data. I mean, I could be on a virtual machine and you are on a virtual machine. I don't know you, you don't know me, but we are completely isolated from one another. I could be running an e-commerce website and you could be running your own personal website, and we don't know about the fact that we are next to each other when it comes to compute that we are using in the cloud. Now let's say we have a private cloud that belongs to the customer and a public cloud. Now the customer decided, okay, if the private cloud fails or there is a major problem, then I'm going to shift into the public cloud. So this will be my backup. Or maybe I'm running out of resources on my private cloud and I would like to use the public cloud for more processing and all that. They call it bursting into the cloud. When you have this type of setup or infrastructure, it would be obvious that maybe some applications on your premises, they need to connect to the cloud, databases on the cloud, and they would access this data. Or the other way around, applications on the cloud, they need to access database on premises or in your private cloud. Or maybe developers sitting somewhere in your offices, they would like to come through the office and then connect to the cloud in order to ensure that whatever they have been appointed to perform is working properly or is installed or is running, or maybe troubleshoot a problem. So in that case, you need a connectivity between the two, between your corporate data center that is a private cloud, or that's where your private cloud exists, and then the AWS cloud or the Azure cloud or whatever it is. And the connectivity can be over the internet, it can be in a secure fashion over the internet, which we call it VPN, Virtual Private Network, or it can be a dedicated link that you only use, and it has the same performance and the same latency and the same criteria all the time. So this is what makes a hybrid cloud, which is the mixing or the combination and connectivity between a private cloud and a public cloud. Okay, now the question that comes to mind, okay, so I will have this kind of setup, but now how can I automate and orchestrate? Now I have maybe pre-built my private cloud and the automation and orchestration that is not AWS. Now I want to connect to AWS. Now we maybe require an automation orchestration on top of the two in order to do that. So that's the complexity when you start mixing cloud types. Okay, but of course it is cost effectiveness because I could use the resources I have and then burst into the cloud. Okay, so the public versus the private versus the hybrid cloud is what we see on this picture. The public cloud provider data center, and then we have the private cloud or the on-premises data center. And when we connect them together through the internet or private connectivity, they become the hybrid cloud. I have users that might be coming through the internet to connect to my public workloads. And when we mean by workload, we mean applications and whatever you have hosted in the public cloud. And maybe also I have private cloud users that are coming. They could be the employees of the company, for example, and that's how it looks like. And of course, I will need an engine called the identity and access management in order to find out who is supposed to access what and what actions they can or cannot do. Then we have a shift, which is the multi-cloud, or a new trend that is the multi-cloud. Companies have found that there is no one public provider fits all. So maybe one is cheaper than the other in a service, maybe one is better than the other in a service, and the companies, especially the enterprise, they need multiple services. One is better in artificial intelligence, another one is better in search engines, the third one is better in databases, the fourth one is better in terms of connectivity and global presence. Then they started putting different workloads on different clouds. And that is not a bad thing because I could be saving costs, I could be getting more performance and efficiency for my dollars. So when I end up doing this, then the problem becomes, how can you automate and orchestrate the workloads across both? So that's a level of complexity. And it becomes even more complex if you had a private cloud on premises that has applications or maybe databases that they need to connect into the different multi-clouds that they are using. And now we need connectivity, and that's where the hybrid cloud nature or solution is combined with the multi-cloud, and that it becomes the hybrid multi-cloud. And this is where the industry is going. So all analysts are saying There is no one cloud that fits all, and customers are moving into the multi-cloud, and they have their own confidential data or pieces of data or applications that they cannot move into the cloud. Hence, they end up with the hybrid multi-cloud. Now let's look at the very common cloud services. They call it the as a service model or AAS model. And then they can put infrastructure before that and it becomes infrastructure as a service, or a platform and databases and middleware, so it becomes platform as a service, or the full 9 yards is from the provider, so you are getting a software as a service. Or they call it the XaaS. Why? Because we have function as a service, network as a service, security as a service, data as a service. There's an as a service model, which is basically using services and paying with a bill at the end of the month for what you have used. That's it. We have network, storage, hardware, virtualization, operating system, middleware, runtime, data, and applications. All of these are the components or the different components we might be using. All right. So if we go and use that on premises, that becomes the fully or 100% the customer responsibility. So it's customer managed. So now if you decide to do that, then it becomes your responsibility from a CapEx perspective and also from an operational perspective. And whether you do it yourself or you do it through consultants, it's your responsibility. But when you go or shift to the as a service model and you decide to take a virtual machine from AWS, for example, then you are contributing or subscribing to what we call infrastructure as a service or IaaS. In the infrastructure as a service, the cloud provider will be responsible for the data center, for the network, for storage, for hardware and virtualization, because probably you are using a physical server or a virtual machine. But other than that, it's your responsibility to decide with Windows or Linux, what's the middleware, what's the runtime, what's the data, and what's the application. If we take it a little bit deeper on the cloud, then we go to what we call the platform as a service, whereby the provider is responsible for everything, all inclusive of the runtime. And then you are only responsible to bring on your data, manage it, and then the applications. Or maybe I want to subscribe to something like Salesforce or Netflix, where they have built everything and I just need to use it. I don't need to manage anything, not even the data or applications. So in that case, becomes a software as a service, and you are not responsible for anything. And even if it doesn't work, you just email them or maybe open a support ticket or call them and they will fix it for you. Okay, so these are the most common as a service models, but these are not the only ones. Hi everyone, welcome back. Let's now start our introduction to DevOps. What is DevOps? Why do we use it? What are the tools? What's the benefit? Why should I learn it? Stuff like that. Okay. Before we understand what DevOps is, let's understand what the software development lifecycle is. Okay, and that is nothing more than the framework that developers and companies producing software or enterprises are using to create software applications. And usually this number of steps in the framework, they could be planning, we want to make an application to do such and such. Then setting up the teams and starting to build the code. And then building the application from the code, and then testing to make sure that it does what it's supposed to do, then releasing the software or the version number, and then deploying it, and then operating that to enhance it and optimize it, which goes again through planning to enhance, and then coding, and then the same thing again and again. These steps will help us in dividing the entire software development process into tasks that can be assigned, completed, and measured. So basically, throughout the project, you can manage it and you can make sure whether it's going on track or it's behind. If there are bugs and software problems or issues, and you do testing and you provide feedback until it is ready. So that's a framework, an architecture, roadmap that we have to follow in order to get from the idea until there is a product. Okay? And why do we use a framework like that? It will provide us a measurable way of providing or developing these softwares and measuring also whether we are efficient or not efficient, and we can improve on that. It also will provide us an accurate analysis for every step. And also it will facilitate faster software delivery as opposed to just working randomly without anything to govern or manage the entire project. And also that will ensure better quality for the software and better user experience at the end because the software is meeting the expectations. So as we mentioned, the software development goes through these steps that we have talked about. And most important is we do frequent testing and we provide feedback to the developers so they can reiterate until we have a perfect software, hopefully a perfect one, not all the time. And then releasing and deployment. Okay, so we need to minimize the human factor, because if there's a lot of manual stuff happening, then we might have a lot of errors. We are human and human beings make mistakes, right? So we would like to automate that process, and DevOps is all about this automation, bringing the operation closer to the development in order to ensure that they are working hand in hand and they can find out any issues as they arise, fix them, and move on. This is as opposed to having the developer work on everything and then they say, okay, we finished the code. Now it is for the testing team that we have nothing to do with the testing team. And then it goes to the operation and we have nothing to do after that with the operation. So instead of pointing fingers, work hand in hand as a team to ensure that we get to the deployment and operation and optimization without any issues. Okay, so the older way was we have walls between the different teams, and the new way is no, we need to work collaboratively and we need to work in an iterative process in order to make sure that so we reach our targets very fast with high quality, less errors, and also to make sure that they work hand in hand instead of pointing fingers at one another. Okay, there are many ways or distinctive methodologies that are used for developing software or managing software projects. And one of them was the old one, the waterfall and agile. And if you compare them side by side, we'll find that the waterfall used to have an analysis phase where all the requirements are gathered and then they start planning, designing, building, testing, and deploying. The problem with the waterfall is it's once it kicks off and starts, it doesn't stop. It doesn't take new input and it must finish the milestone before getting into any requirements gathering again. The agile method, it's all about an iterative process, a continuous process where we do everything again and again. So if we look at the waterfall, we are gathering requirements and designing, then coding, testing, deploying. But in agile, it says it doesn't work that way, because that means we may have a lot of surprises when we do testing, because we have been coding for a long time without integrating the code from the different development teams. So why don't we code a little bit and then test that, bring the code from the different teams. Let's say they finished one milestone. Then after that milestone, we bring in the code, we test, and we find out, okay, the expectation after this milestone, we should not have this or that problems. And we found out that we actually don't have them. So, okay, let's go ahead. So we integrate, test, code again, and then test, get feedback, and then code again and test, and so on until we deploy. So it's an iterative process where we repeat all the tasks again and again as we move on. Imagine that this is a tire or a wheel that is revolving, but also moving forward towards the goal of finishing the product. Okay, so the iterative nature of Agile made it much more popular than the waterfall. The waterfall is when something happens, it doesn't repeat. So the water comes from the falls, it goes down, then it hits probably some rocks, and then it moves horizontally, then it falls down, and so on. Okay, waterfall, as we mentioned, is a sequential methodology, and it is not the preferred one. So what's the DevOps? DevOps is all about, as we mentioned, bringing the teams, the operation and development together and having them work hand in hand through the SDLC, through the software development lifecycle, to ensure we have a better product faster with less errors and achieve the highest user experience or the highest user satisfaction. Okay, now, one might think, okay, so DevOps and Agile, why are you comparing the two? And we say that the DevOps, because it's automated, it allows us even to do more and more of these cycles, the code test. But not only that, but also we do code test and deploy. Then we need another feature, or users are complaining about something. And then we do again, coding, testing, and release. So we do more releases, and it could be multiple times a day. And now we have everything startups on web apps. So these apps, you will find a lot of updates. It's asking you, okay, updates are ready. Okay, install. Same thing happens, for example, with Android or with iPhone. You find a message that says, okay, update is available, install, or maybe later on. And it depends on how it is critical. So that's what we need, and that's what the software application companies need. They need to be able to take the feedback from the customers, enhance and optimize, and provide a better user experience, and hopefully we can achieve that multiple times a day. So Agile and DevOps are different things, although DevOps does use the iterative process, but it does do a lot of deployments and a lot of releases as well, compared to Agile only without the automation. Okay, so when we use DevOps, we can achieve a lot more than if we used only Agile without the DevOps part. So when we use DevOps, we can achieve a lot more than if we just do Agile without the DevOps. Okay, so please keep this in mind, because you might be asked the questions. We are already using Agile. Why should we move into a DevOps? Let's now get to understand some of the important CI/CD concepts that we will come across. Before doing that, let's reiterate or recap what we said about what happened before CI/CD. So before CI/CD, developers and the operation team, they used to work in isolation from one another, and also developers used to work for extended periods of time working on their code without any integration with the other teams or the other developers. Okay? And they used to integrate or merge the code less frequently. They did less testing, which means they also discovered integration issues that were more complex and took longer to fix because of the fact that they did a lot of code before they started integrating with one another. So CI/CD, what is that? CI/CD stands for continuous integration, continuous deployment, and continuous delivery. So the CD is continuous delivery or deployment. The CI is the integration part. These are software development practices or best practices that are aimed at automating the process of or the software development lifecycle of the software products. So we need to improve the software quality, and we need to integrate more so we can speed up the testing and discovering bugs and fixes that are early in the process so they can be fixed quickly. And that means we can do more deployments and more releases at a high quality, thus enhancing the overall software development lifecycle. If we think about continuous integration to start, so this is a DevOps software development practice. What does it aim at? It aims at integrating or merging the code more frequently from the different development teams or the developers in a shared repository, and then we build the application, or we build that part of the application by integrating that code and then doing testing to discover bugs and then provide feedback to the developers. So that means developers need to push their code more frequently into that shared repository and then gets merged with the main code, and hopefully without any issues or anything. Then we start the validation and code testing. So the first thing is they commit code changes to a repository, let's say GitHub, for example. And then the CI tools, that part or the tools that run the CI part, are going to start building and then testing. So the CI/CD pipeline is basically taking from the time that the developers start committing their code into a repository and then merging the code, building, testing, and then hopefully if that cycle goes and then some iterations happen and then we have a clean code, then we go into the deployment or the release. So these two, or the CI and the CD part, is what we call the pipeline or the CI/CD pipeline. On the other hand, continuous delivery and continuous deployment. What's the difference between the two? The main difference between the two is do we release only and then wait for approval or wait for the proper time to come and then deploy that release, and that is continuous delivery. If there is human intervention or human interaction to either trigger the delivery part, the provisioning part, the actual deployment, or to pre-approve it before it goes into production, then that's continuous delivery. But if we get from the CI and then there's a continuous deployment, which means the software is ready now and then it goes automatically to be deployed without any human intervention, so that becomes continuous deployment. Okay, so the CI has done the building, the merging, building, and testing, and now everything is clear. We went through the iterations and everything is okay. Now we get into the staging deployment phase or step in the pipeline. And then if it is continuous delivery, that means we go through manual intervention or manual trigger in order to deploy, or we go with a continuous deployment where the changes that pass all the CI and gets into the staging is going to be automatically deployed without any manual intervention. Let's now look at the most common CI/CD tools. We have Circle CI, Bamboo, we have Travis CI, and then we have GitLab, we have Buddy, we have Argo CD, we have GitHub Actions, we have Jenkins. A lot of famous and known and commonly used tools, but when you get into an enterprise or into a company, you will find either one or two tools at most that are being used. So do you need to learn all of these? And the answer is no. You don't need to learn all of these. You need to learn what you are going to use. The concepts are the same, but it's only about getting adapted to a tool, and there could be some subtle differences between this and that. So suit yourself, find the one that matches what you need, learn it, master it, and you can keep going. And you can from time to time kind of play with the other ones or read about them, use them to find out in test and development environments whether they are better or they will add to what you're doing, or maybe they are easier to use. And of course, if we look at the actual landscape of DevOps tools, and you'll find hundreds and hundreds of tools, and you don't need to learn all of these. You need version control, you need to cover the CI with the products that matches what you are doing, and then you need to cover the CD also in the pipeline with the tools that matches what you are looking for. And that's it. Nobody knows all of these. And of course, if you change from one job to another, maybe you learn more tools, and this is how you learn many of these tools. But I don't think there is anyone on the planet that have used all of these. And if there is one, then he must have spent, I don't know, 10, 15 years jumping between a contract to another contract to another contract to another contract in order to use all of these. And I don't think anyone would have mastered them all. Okay, again, the DevOps tools ecosystem, and what you need to do, as we mentioned, when it comes to deployment, you need to learn one. When it comes to visualization and containerization, you need to know Docker and Kubernetes at least. And then when it comes to reports and all that, you need also to find out a tool that will help you with that. Test automation, and then when it comes to static code analysis tools, build tools, CI/CD tools, scripting tools, so Python, Bash, Perl are examples of that. All right, so you don't need to know everything, but you need to know one that will help you with scripting, one that will help you with CI/CD, one would help you with the build, one would help you with the monitoring, one would help you with the containerization and visualization, and you should be good to go. And the job also may dictate what tools you need to learn. So you don't have to go and find out this or that. But definitely you need to master one of each in order to be able to at least understand the concept, have a way to deploy it, to do some projects before you start your DevOps career. So now the buzzword, cloud native applications, cloud native infrastructure, cloud native service, cloud native this and that. What is that? What is meant by cloud native? And there are two definitions, the CNCF, the Cloud Native Computing Foundation, and also from VMware. So cloud native in CNCF, they say that these are cloud native technologies empower organizations to build and run scalable applications in public, private, and hybrid clouds. So these cloud native technologies, they will help you successfully deploy your stuff on the cloud, basically. Okay, so what are these technologies or these features? If you are using containers, if you are using service mesh, microservices, if you are using immutable infrastructures, declarative application programming interface APIs, these are some of the technologies that if you are using, you could be labeled as a cloud native implementation. But if I'm using these on premises, is that cloud native? And the answer is no. Cloud native means something that is built and is taking advantage of the facilities and technologies and services that have emerged with the cloud, basically. So that's what cloud native is all about. Okay, VMware defines it in a little bit different way. Cloud native is the approach to building and running applications that exploit the advantages of cloud computing delivery model. And if you think about it, it's more or less the same thing. And then they speak about the same thing. You are using public, private, or hybrid clouds, and how your applications are created, deployed, not where. Okay, so that's slightly different, but still talks about the cloud again. And if you are using DevOps, if you're using continuous delivery, microservices and containers and the monitoring tools and delivery tools, you should be cloud native. So it's more of, are you using the technologies that have emerged with cloud? Are you using DevOps? Are you using more automation? Are you having monitoring embedded with your containers and microservices? And if that is the case, then you are using cloud native, or you are cloud native. Okay. Now, when we talk about cloud native applications, that means we are talking about independent services that are packaged as lightweight containers. So you must have containers, you must have Kubernetes, which is the best tool to run that, or maybe OpenShift. And they are often delivered in DevOps pipelines that includes CI and CD. Okay? So cloud native, use whatever buzzwords that are happening today, you become cloud native. I mean, more or less. Then we have another buzzword, which is DevSecOps. So DevOps, we said it's the marriage between development, IT operation, and application delivery. So the intersection between the three is what the DevOps are. And guess what? Add to that the security of the pipeline, the security of the application, and it becomes, the intersection becomes the DevSecOps between the three. And then we have the infrastructure as code, a very important component in the DevOps, and that is defining or describing your infrastructure as a script, as a code that is written, and it can be deployed into cloud computing environments or different, or even on premises. So infrastructure as code means that you manage your IT infrastructure using configuration files, or the description or the scripting files. Okay, and IAC, sometimes it's called infrastructure as code IAC, or infrastructure as a code. So either this or that, it's IAC or IaaC. That's the process of managing and provisioning computer data centers. So the entire data center can be defined into configuration files that can be used, as opposed to using physical hardware configuration. So someone gets dispatched to start configuring and deploying and all that, or even interactive configuration tools like the AWS Management Console or portals and all that. So that's what infrastructure as code is, and that's very important. And Terraform is the most famous one, or the most common one, and is vendor agnostic. So it can work on AWS, on Azure, on Google, on Alibaba, on IBM, or even on premises as well. So if we look here, what the developer or the scripter, I would say, or even the ops person, he will write the code. So he writes the script and which describes the infrastructure, and that then gets pushed into the infrastructure where it gets deployed. So it might be a cloud or on-prem infrastructure, and both of them would work, and then you get management, you get responses. It got deployed right, there were problems, there were errors and all that, and you troubleshoot, fix your code, and then you go ahead. And of course, that code with versioning control like Git and GitHub, it can even manage the different versions of the configuration files using these tools. Now let's find the buzzword SRE, or Site Reliability Engineer, and how is that different from a DevOps engineer? Of course, we are not going to dive deep, but at least you need to understand. Why would you want to become an SRE as opposed to a DevOps engineer? Or why would you want to be a DevOps engineer and then move into an SRE? So why do we need the SREs? Or why do we need site reliability or reliability engineers, basically? Okay, so there is one thing that is a fact. In software development, developers are keen on finishing and pushing their code quickly. So doing more frequent releases. While the operations team, they always are keen on the stability of the system more than deploying every time there is a new release, just go ahead and deploy it. Okay? And DevOps focuses more on the first side, on the speed and stability of releases, but not on the operation side and monitoring what happens into operation. So it could be that DevOps thinks that this is 100% clean. When it gets deployed, then we have problems. So DevOps does not define who takes care after the deployment. And that's where the SRE comes into play. So the SRE is a practice, or Site Reliability Engineering is a practice where the software tools are used to automate the operational side and the application monitoring. And this is how we can ensure it's not only that we have made or optimized the CI/CD pipeline, but also beyond that, we can look at the monitoring, we can find issues, and then we can give feedback in order to enhance the process. So you can look at the site reliability engineer as someone who can probably be engaged in DevOps, but also engaged in the monitoring part and ensuring that whatever is deployed is even enhanced more than the DevOps. Now, depending on the organization, they could be completely different teams, or they could be integrated teams, or maybe the senior people or the lead engineers, they will be entitled to look into the monitoring and the well-being of the releases after they have been deployed, not only throughout the DevOps process. So just to quickly recap, the DevOps is more of a culture than a set of tools. It's agreeing that we need to automate, we need to enhance the process, we need to improve the software development lifecycle, we need to be able to release more frequently, but also more accurately with less issues and problems in the software. So it's not just the tools, but it's the whole concept or the whole culture that needs to be adopted in order to look at this part of the automation and then site reliability engineering as integral components of the success of the practice or the company or the enterprise or the different teams within. So it's more of a culture than just using a set of tools and that's it. And now it's time to talk about TCP/IP addressing, TCP/IP protocol, related information, and also IP routing, switching, a lot of technologies, protocols, or use cases that we use in IT. It's good to have a high-level information about that, because as we start learning cloud computing, we will get into the networking side of things. And if we have that high-level introduction, I think our learning is going to be much easier. Step back, as usual, and let's now introduce something called the binary numbering system. We are all used to the decimal numbering system. 10 plus 10 is 20, 10 plus 5 is 15, 2 times 3 is 6. I mean, we deal with that day in, day out. Even when we are dealing with money, we calculate it that way. I mean, 20 bucks plus 15 bucks is 35 bucks and so on. So why do we need to learn another binary number system? And trust me, we're not going to learn it or master it. We just get an idea because IP addressing is related to it. Second thing is because everything inside our phones, computers, iPads, and laptops, and so on, it's all binary. It's all digital and it's all binary. And the binary numbering system, unlike the decimal numbering system, it has only two symbols, the 0 and the 1. In the decimal numbering system, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the symbols that are used to build any decimal number or any integer, basically. We're not talking about dot something or dot 5 or 0.5, or I'm talking about decimal numbering system as a whole. So computer systems and digital devices, they all use the binary numbering system in between or inside them. And when we use decimal numbering system in our application, so you are using a calculator on your laptop and you type 15 times 5. Guess what? Inside the laptop, this is going to be converted into the binary equivalent of 15, binary equivalent of 5, and then a digital operation is going to happen to multiply them and get you the result. So you enter the numbers as decimal, and the result is going to come out as decimal as well. For example, if we have the number 204, the binary equivalent is going to be 11001100. Don't worry about that. If you have any calculator or even on the internet, just write down what's the binary equivalent of 204, and you will find this is the equivalent, the string of ones and zeros on the screen. Each one of these ones and zeros is called a bit, a binary digit. Okay, so this string has 8 bits. 8 bits are equal to 1 byte, or we call it an octet. Let's recap our web application, the client server that we talked about, and find out if I am on the internet using a digital device, a mobile phone, a laptop, a desktop, whatever it is. And then there is dolphinet.com. When you open your Chrome and then, or Safari or whatever, and then you type www.dolphinet.com, magic happens. You don't see it, you don't know what happened, but you are going through the internet and you get the page of dolphinet.com. How did that happen? How did my request to open www.dolphinet.com get to the right IP address on the server or the right location of the server? And how did the response from the server make it through the internet to me and it did not mistake me to someone else? How did that happen? And that's because of what we call the IP addresses. So the IP addresses is my address on the internet and your address on the internet. Exactly like if you have a mailing address and I have a mailing address, we can write letters and send them to one another. Or maybe you can send me a gift and I can send you a thank you letter. Also, on the email side, you have an email address, I have an email address. You write the email address, so you become the sender, I am the receiver. It gets to me, now I type the response and I click on send or submit, and that brings that back to you. So two things happen. You have to have an IP address, or your machine or your client or your phone has to have an IP address on the internet. And also the server has to have an IP address on the internet, and they must be reachable IP addresses. Reachable in the sense that they are accessible from the internet. That's what reachability here means. But who does the actual routing? Who takes it from your laptop or mobile phone or iPad and then forward it until it gets, so you are in the US talking to someone or a server in Japan, and who gets it all the way to Japan and brings it back? That's what we call the IP routing, which is enabled on the internet. So the internet is nothing more than a lot of devices interconnected at high speed, and these are called routers. These are actually giant routers that are responsible for forwarding all the traffic that happens second by second on the internet. So IP address on the server and the client, and we need IP routing. That's the whole magic that happens. And of course, you need the Chrome or the Safari browser, and on the other side we need a web engine. It could be an Nginx, it could be an Apache, it could be an equivalent one, something that can build a website and listen to the request and then build the responses and send them back. Okay, so IP addresses are needed because these are the addresses. This is how you are known to on the internet, and that's why we need an IP address, and every device on the internet has an IP address. So what if I'm connected to 5G or 4G network, I'm on the go and I have my phone, data is activated, and I have access to the internet. Does the phone have an IP address? And the answer is yes. I'm connected with my iPad at home to the Wi-Fi and I'm connected to the internet. How does that happen? Again, you have an IP address on your device. So there is nothing happening on the internet or on any infrastructure enabled for TCP/IP forwarding and transmission without IP addresses. TCP/IP stands for Transmission Control Protocol / Internet Protocol, TCP/IP. Okay, so your IP address is like your business address or your home address, and that's how people can deliver packages to you. Okay, and exactly like we do with human beings, that everyone has an IP address with a city and street number and an apartment number if it is a building, and then the state and the country, same wherever it is. Then we do the same thing when we are talking about clients trying to speak to a server or servers trying to speak to a server. Everyone has an IP address, and that's how they communicate. IP addresses, they could be public, they could be on the internet, accessible through the internet. And as we will learn later on, we have private IP addresses, the ones that we can deploy inside a building without being exposed to the internet, or we need a converter in order to have them reach the internet. There are two major types of IP addresses, and they are the IPv4 and the IPv6. The IPv4 is the one we are using mostly now on the internet, and it has been in the use for about 30-40 years now. And it's in decimal notation. It's 32 bits long. Remember, what's the bit? It's a binary digit, the 1 or a 0. So 32 bits long. And as we mentioned, a string of 8 bits constitutes what we call an octet or a byte. So the IP address is 4 bytes or 4 octets long, or 32 bits long. They are the same. And an example is 120.1. An example would be 120.130.233.12. So this is a string of 8 bits, a string of 8 bits, a string of 8 bits, and a string of 8 bits. Okay, in the binary notation. And the number here in any one of these octets cannot exceed 255 and cannot be less than 0. And it requires something we call a subnet mask. We'll learn why. And it can be public or private IP address. On the other side, when they were worried that the IPv4 is going to be depleted, IPv4 addresses are scarce already and there isn't plenty available. And there aren't plenty out there to be enough for everything happening on the internet. So that's why they came up with IPv6. And it's not in decimal, it's in a hexadecimal notation. Another numbering system. And it is 128 bits long, 4 times longer than this one. And it has 8 fields. Each one of them is 16 digits or 2 octets. Here it's only 4 fields. Each one is 1 octet. Here we have 8 fields and each one of them is 2 octets. And here's an example. And as you can see, it's much more complicated compared to the IPv4. And it requires also a subnet mask, but it's all public. There is no private IPv6 addresses. Why there isn't an IPv5? Ask the ones who came up with the names, the scientists who worked on that, and they will tell you why. I don't know why. Okay, so now if we revisit our client and web server, then we have a server with an IP address and a client with an IP address. And as if we have 2 with the name George in the same room, and if someone comes in and says George, both of them are going to look at the person, or maybe both of them are going to respond. And the same analogy happens on the internet. If we had the same IP address available on 2 servers, then which one would respond? That's why there are no overlapping, there is no repetition of public IP addresses on the internet. So there is no way there will be someone using the same IP address as the other one, unless if it is a hacker trying to pretend to be someone, but then the routers on the internet are going to be intelligent enough and they should stop it. So how can we regulate that? How can we govern that and control it? There are something or entities called internet registries, and these are the ones appointed in each continent to hold the range of IP addresses or be the representatives of the ones who hold the available ranges or the available space of the IPv4 address. And you have to submit a request. You have to send a justification. Why do you need the public IP address range? And then they will decide to give you 8 or 16 or 32 or 256 or more or less. All right. So it's all governed, and everyone should have a unique public IP address on the internet to be accessible through the internet. And then of course we have the IP routing that we are going to cover later on. Okay, and if you are on a Windows machine, you can use from the command prompt ipconfig to find out what the configuration is or what's the IP address. Or if you are on Mac or Linux, you can do ipconfig get interface address Ethernet 0 or EN0, and you should find your IP address. Okay, now let's find out if we have a building and I'm sending a letter into that building, 32 St. George Street, Toronto, Canada, for example, and the postal code. Now, if it gets to the building, 32, that's a high rise. It has like 40 stories and maybe 200 apartments. Then which one should get it? Who should get that? That means the IP address that you have, if we take that analogy and then draw it to the IP addressing, if I have a network with multiple servers, then I should be able to address a server on that network. It cannot be that I'm going to send to all of them. And that's exactly the case. Every IP address has what we call a network part and a node or a host part. So let's take the one on the screen as an example. We have 192.168.1.2, and then with any IP address, there is a slash and then a number. This number can be anywhere from 2 or from 1 even to 32. It cannot exceed that. Why? Because that number signifies the following. That number can allow any device or any machine or any server or any router to find out where is the network part and where is the host part. Remember when we said that any IP address is 32 bits long, 8, 8, 8, 8. Each one of these fields is 8 bits. When you have a /24, what does it mean or what does it signify? It signifies from the left-hand side, count 24 bits. So that's 1 octet, that's 8, 8, and 8. So that means the first 3 fields on the left-hand side, this is the network part. And the remaining, which is the 8 in this case, is going to be the host part. So here, that this is the network, and that's a host on the network. That's an apartment in the building. That's a house in the street. So the street is one thing, and then which is the network, and then each house has a number in that street, or has a host in that street, or a node in that street. So what can tell the computers and the networking devices and all that, what is the IP address of the node and what's the network that it belongs to? That's the subnet mask. And the length, as we mentioned, it can be 8, it can be 9, 10, and so on. So anywhere between 1 and 32. And the binary equivalent of this number is this string here, and this is 8 bits, 8 bits, 8 bits. The one in white, this is the network, and then this is the host in this case. So if it is 3, then this is going to be different. If it is 4, then this is going to be different. So the same network can have multiple hosts or multiple nodes into it. Okay, what if the number is different? I mean, it's 192.168.1.2/16. If it is /16, this means that the network is 8 and 8. So that's the left 2 fields. And then the right 2 fields are going to be the node or the host. And the subnet mask is the judge. It's the one that decides which one is the network and which one is the host. Okay, and here's the equivalent and the network part and the host part. What is the network component of an IP address and what's the node or the host component of an IP address? Now let's get into the subnet, something called subnetting. And in order to understand subnetting, we have to understand something called CIDR or CIDR, the classless interdomain routing, and that's a CIDR range, a block of IP addresses. And examples are 10.0.0.0/8. What does that /8 mean? The first field is the network, and anything that goes here is the host. /24, the first 3, 8, 8, 8 are the network part, and then we have the host part. So the host part can be 0, 1, 2, all the way to 255. That's the maximum. And then we have 120.100.0.0/16. What's the /16 signify? It signifies that the first field and the second field is the network, and then the 2 others are the hosts. Okay, so what's the notion or the meaning of subnetting? Subnetting means I have a block, a big network, and I need to splice that into multiple networks. So I have an orange that I want to equally divide into 4 quarters. And usually the subnetting, when you have a range and you want to divide it, you can divide it into 2 or 4 or 8 or 16 or 32. Can I divide it into 5 equal parts? No, you cannot. But you can divide it into 8, use 5, and then 3 will be spare or backup. Okay, I need 12. Can I do 12? No, you cannot. You can do 16 equal parts, and then you use 12 of them, and then you have 4 spare. That's how it works with the subnetting. It has to be divided into the multiples of 2. 2, 4, 8, 16, 32, 64, 128, 256, and so on. Okay, and here we have an example, 10.0.0.0/8. I want to divide it into 2 equal ranges. What do? That means I need to increase the subnet mask from 8 to 9, and that will give me 2 different fields. How can I get that? Easy. I mean, we can do the math, but that will take us a long time to learn. But we can do the online subnet calculators, which are going to help us do that and achieve that as well. So let's go ahead and do some exercises about this and find out how it looks like, what will be the equivalent ranges, and what would be resulting subnets or the resulting equal parts that we are going to have. Okay, so here is an IP address range or a CIDR block, 192.168.240.0/24. Now we are the experts. /24 means 24 bits from the left-hand side is the network part, and then whatever is left is the host part. So the 192.168.240 is the network part, and then this is the host part. What is required? Required is to split this orange CIDR block into 4 equal pieces. As we mentioned before, if we put all the values of the hosts here, the minimum is 0 and the maximum is 255. So that is a complete 256 different combination in the host part. 0, 1, 2, 3, 4, 5, 6, 7, 8, 20, 21, 22, 100, 200, 254, 255. So if you count these, including 0, these are 256 different numbers. So if I want to equally divide that, use your calculators, please. 256 by 4 is 64. So the resulting is going to look like that. It's going to be from 0 to 63, these are going to be the first 64 numbers, and then from 64 to 127 is going to be the second, the third equal part, and the fourth equal part. Of course, the numbers are different, but they are 64 in each one of these. And that was the requirement. And as we mentioned earlier, we can divide by 2, we can divide it by 4, by 8, by 16, but we cannot divide it by 6. We cannot divide it by 3 or by 5. And the subnet for each one of these is going to look like this. So the resulting quarter of the orange of the CIDR block is going to be, the first one is going to be 192.168.240.0. The second one is going to be 192.168.240.64. And the third one is going to be .128, and the fourth one is going to be 192. So the network part did not change in all of them. However, now I have 4 distinct subnets that each one of them has a start and an end, and they are only 64 hosts in each one of them. So as if I had an apartment of 4 bedrooms, and then I divided these 4 bedrooms and I had an external door to each one of them, and I blocked the common doors, and now they are completely separate. That's exactly what we did here. And the subnet mask is going to be a /26. Why? Because if you want to divide by 2, the subnet mask of the resulting halves is going to be /25. If you want it from your original subnet mask to divide by 4, so that means the subnet mask is going to be a /26. Or that means you have taken 2 bits to divide, and there's 2 010001011, or these are the different combinations, so that gives me 4. How about if I wanted to divide by 8? Then you take the subnet mask and you increase it by 3. How about if it was 16? Then you increase it by 4, so it becomes 28, and so on. Okay, to prove that, let's take the same range, and we are going to go into this website, and let's play a little bit and see if what we did is right or wrong. So if you click on that page, you get into here, and then here we are going to put the IP address as 192.168.240.0. The initial subnet mask was what? Exactly, the initial subnet mask was /24. So what I will do now, so /24, I want to make it into a /26. Why do you want to do it into a /26? Because I said if I want to divide by 4, I have to increase the subnet mask by 2. So let's calculate and let's find out what will be. Oh, I'm sorry, it doesn't like the subnet mask here. That's fine. So let's calculate now, and here we go. So here is the IP address, okay? And here's the first range. So it starts, the subnet starts from 0, and then .1, .62, .63. So these are the available ranges. Forget about what the broadcast is now, because we don't want to talk about it right now. It's not relevant. Total number of hosts or nodes in that subnet is going to be 64. And the subnet mask is going to be /62. And then we have the other 3, 64, 128, 192. And it gives me that this one starts at 64, so that's 65 all the way to 126. And then I have 127 as what we call a broadcast address, and so on. So here they are saying all 4 of the possible /26 networks for 192.168.240 are these ones. What if I wanted a /25? How many parts am I going to get? So we shifted the subnet mask, we increased it only by 1. And that, believe it or not, is going to give me only 2 halves. And these are the 2 halves. How about if the range was different? Let's say it was 10.0.0.0, and the original subnet mask was /8. And now I want to divide it into 8 equal parts. What do I do? So that means I need to take the /8 and increase it into 11. Why? Because we said we have to increase the subnet mask by 3 if you wanted 8 parts. And here we go. 1, 2, 3, 4, 5, 6, 7, 8. So this is your guide, your helper, if you want to go and calculate the subnet masks. There is a lot of math behind it. You don't need to waste your time on that. But now you understand, if you are given a CIDR block, a range or a block of IP addresses, you can be smart and you can divide it. Why would I divide it? Because it's not advisable to have 2,000 or 200,000 nodes on the same network. So what we do is we divide them into a smaller subnets or networks, and then we divide our hosts, so we can also have an application segment, and we can have a database segment, and we can have a web segment, and we can have a secure segment, and then we can apply devices in between to connect them, and these devices or network devices are going to apply security and ensure who is talking to whom. If one segment is compromised, not necessarily the other ones are going to be compromised, but if they are all on what we call a flat network, they are all nodes or hosts on the same network, then if one system is compromised, the others can be compromised as well. All right? And also, if we didn't have that, imagine how many million devices or maybe billion devices are on the internet today. Imagine if they were all sending their traffic on the same network, and any one of us can try to hack any other one because there is no security, no isolation, nothing between us. And that would have been so risky, and the internet or the traffic on that network would have been humongous to a point where maybe all of us would have suffered even to communicate. All right, so segregating and distributing that into separate smaller networks across the globe is how the internet is still functioning properly right now, and also how we can isolate and protect the different segments from one another and from the external sources, or even maybe from the internal sources. All right, so that's something that we need to know by heart, and this calculator should be your best friend. There are different classes of IP addresses, and this is just for your knowledge. So if the leftmost octet starts with 1 or up to 126, this is called class A, and the common subnet mask in class A is /8. So we have more hosts than networks in a class A IP address. If the leftmost octet is 128 or 129 or 130, all the way between 128 to 191 inclusive, then that's a class B, and the common subnet or the starting subnet would be a /16, and it's balanced between the number of hosts and the number of available networks. And then a class C, which is when the leftmost starts with 192 and goes all the way to 223, and the common subnet mask or the starting subnet mask is /24. It has less hosts on each network, but has so many networks. Okay, so this is just for your knowledge. You're not going to be asked about this in an AWS exam, a project, but maybe in an interview, especially if it is a junior job and they want to validate your networking skills. Okay, now here's a table that tells you if you want to divide your range by 2, then you just increase by 1, they increase the subnet mask value by 1. So if it is /24, we make it 25. That's the subnet mask. How many subnets are going to be resulting? It's dividing by 2, so that's 2 halves. And then it shows me if we are starting with a /24, so that there will be 7 bits left for the host, or in other words, each one of the 2 halves can have up to 128 IP addresses. If you want to divide by 4, so we increase it by 2, the subnet mask becomes /26, and then the number of resulting subnets are 4 equal ones, and the number of hosts in each is 64, and so on. So this is like a guiding table if you want to use it. And of course it applies if I started at /8 and I want to divide by 2, so I'm going to increase by 1, so that becomes a /9. If I want to divide by 4, so that will become a /10, and this is going to be the subnet mask. So the starting subnet mask length, increase 1, that means dividing by 2. Increase 2, that means dividing by 4, and so on. Okay, now let's talk about public IP addresses, and we said public or internet routable IP addresses. That means they are assigned by internet registries. You cannot just deliberately use any one of them. And if they are private, there are private ranges that anyone can use, but don't send them on the internet because they will not be routable, and the internet routers are going to drop the traffic sourced from private IP addresses. You can use them without any permission from anyone in your network, in your enterprise, and all our Wi-Fi devices at home, believe it or not, they will be using the 192.168 range because it's a private one, and that's how the IP addresses inside your home are going to be from this range. Okay, I can use the 172.16 all the way, so I can use 172.17, 18 all the way to 31, and I can use the 10.0.0/8 without any permission from anyone. And here are a set of quick subnets that you can use deliberately without even going and asking permission from anyone. And these can be applied also on AWS, but now you also have the subnet calculator. So if you are given a range and you want to divide it into 4, into 8, into 16, into 32, then you can do that. Or these are ready-made ones that you can use them and go ahead and work with them. If you wanted a fourth one, that will be .4, .5, .6, and so on. So in practice, in real life, if I'm doing this, how would I design it? How am I going to go with a /28 or a /15 or a /24? What do I do? Usually in real life, you would ask the question, how many segments do we have? They will tell you this is application X, application Y, database 1, database 2, and this is for demilitarized zone, and this is for connectivity to the other sites, and this is for the branches and all that. So you will gather all that information, and then you ask them, okay, in that building, you needed one subnet. How many users are going to be in that building? If they said 2,000, 3,000, say, no, that's wrong. It cannot be one subnet. It has to be divided. You can have 128 maybe, you can have 256, but not more than that. And the lesser, the better. Now they tell you, okay, fine, we're going to go with 250 users in each subnet. And then you say, okay, I know that. I'm going to go with a /24, and that will give me 255, as Isa told me, and that should be enough. And the answer is you're wrong. Because if you do that, and then they hire 20 more employees in that subnet or in that department, what are you going to do? Are you going to reconfigure your infrastructure again? So when you do the practice, if they told you we need 250, make each subnet a 512. What would be the 512? That's a /23 subnet. Do the math or go on the internet calculator and you'll find that. So you usually leave some space to grow, to scale. That's very important. If they told me we need 30 subnets, okay, that's the maximum we are going to use on day one. I say, okay, fine. I'm going to divide that into 64, use 30, and you'll have 34 more for growth. Or maybe I'll divide it by 128. You use 25 of your capacity in day one, and then you can grow 3 times that in the next 5, 10, 15 years or something. So always plan for the future and don't limit yourself to what is required, because readdressing an infrastructure is a nightmare. You don't want to get into that trap, and you don't want to migrate all your infrastructure just because whoever did the IP scheme, planning or designing the IP is called building or designing the IP scheme. If that person did not do the due diligence, that is going to be a big issue in the future. Now let's look at what we call routing and switching. Introduction to routing and switching. Now we understood that we have IP addresses and we have subnet mask, and we can be given a range and then we can divide it. Okay, perfect, very good. Now we mentioned on the internet between the client and the server, there are 2 things. There's the IP addresses and also there's the IP routing. So let's learn at a high level what that is. Okay, let's first start with the LAN, local area network. What's the local area network? That means connecting multiple devices in a data center. It could be application and database, and they want to connect in the data center because the users will come from the internet and get into the website, and from there they are going to get into the applications and database and all that. So building or connecting devices to communicate with one another in a confined area, and that could be one building, it can be one room, or it can be a campus in a confined area. So it could be a university campus, for example. This is called a local area network. And local area networks requires what we call switches to connect them. So you hook them with cables, and they could be fiber optic cable or they could be copper cables, depending on the speed you need and the distance, and you end up with a network. And you could have in your home that you have the Wi-Fi router, and then you are connecting a device wired, and then you have Wi-Fi devices also connected. So every home router has a mini switch. So that means connecting devices in a closer proximity to each other, and that's what makes the local area network. Okay, and the Wi-Fi routers will have a mini switch, as we mentioned as well, and these could be smaller ones like the one we have at home, or they could be the giant ones used in data centers. Okay, what if we have multiple buildings? Then what we do is we connect switches, and then we link those switches with what we call an uplink. So a link that is going to another building or to another entity. And that could be how we do it in a data center. So that's completely high level 101 introduction to switching or local area networks. Okay, great. Now we move into, now I have the data center and I need people to connect from the internet to the data center. What will be the first device in my infrastructure that connects to the internet? Can it be a switch? Usually it is a routing device, a device that understands IP addresses and can make decisions based on that, and they establish databases of destinations they can reach on the same device. Can a device be a switch and a router at the same time? Of course, they can be. So if I need to connect a site to another site, we need a router on each side. Okay, so on each one of these, the gateway, the way out to the internet, or if there's a private connectivity between them, then it's going to be a routing device on this side and a routing device on this side. There's going to be a network and hosts in that network, or maybe multiple networks on this side, and also maybe one or more networks with hosts configured and active in them on this side as well. Can the IP address or the range of the network on this side and on this side be the same? Of course not. Imagine that you are writing a letter and you are saying the sender is, and you put your details, and then you put the receiver is, and you put your details. And you go to the post office and you drop it in the mailbox. Imagine where it will go. It will come back to you, right? So if you want to send it to a receiver, you have to have the sender and receiver be different. So these devices, to communicate with the devices on the other side, they have to sit on different networks. They have to be different hosts on different networks. Now, can this be a host of value 1 and a host of value 1, but on different networks? This is 10.0.0/24. /24 means the first 3 octets are the network, and this is the host. So if the networks are different, the host can repeat. But if we have the same network here and the same network here, guess what? The router will never send it to the other side, because each time the message will arrive at the router will look at where is it going, and you will find out this is going to a device on my network. Why should I send it out? I'm going to just resend it back. So the message will never get delivered. So in order for routers to function properly, they should be sitting on different networks. And that's another good reason why we have subnetting, because if you have a big block and now I need to build a hub and spoke, like a central location where the branches are going to connect to, that means an IP address range is required in each one of the branches, but also another one is required also at the main or the headquarters. All right, so that's just tying everything together. So a routing device is required. What about the one I have at home? Is that an internet router? Yes, it is an internet router. It gives you private IP addresses on the Wi-Fi, and then it connects to the internet with a public IP address, and it does translation as well. Okay, so that's an intelligent mini device basically. Now, if we elaborate on the same example we had, so I have a server with 10.0.1.5/24 on this side. The network on this side is 10.0.1.0/24. So that's the network. And these are the hosts. Any number here are the hosts. And I have a router that has an IP address of .15. So even the router is considered to be a node or a host on this network. That's how it talks to this network. And then on the other side, I have a completely different CIDR block. I have 192.168.1/24 as well. So the 3 octets are the network, and then this is the host. And then I have the router .1.1, and then I have a server here, which is .1.13. Okay. Now, what would be the database look like on this router, and what would the database look like on this router? What is this? This is called the routing table or the forwarding database on the router. So this router will know about 10.0.1.0. And this is through its local area network interface, through the interface connected to the switch. And the router on the other side, it will know also through the local area network about 192.168.1, which is connected here. But then they will exchange the information that each one has. So this router B, will know about 192.168.1.0, which is the other side, and it will know about it from router A. And router A is going to know about 10.0.1.0/24, which it also knows about it from router B. So that means the routers can exchange the forwarding information, and that's how they know about the remote networks and not only the local ones. That's how it works. Now, one might ask, okay, how about the network in between, the one that is on the internet, or maybe the private connectivity? It must be an IP-enabled network as well, and they must have an IP address on each side of this network, and that's how they communicate. So end to end, there is IP processing and IP intelligence across the board. And using these routing tables, routers can make forwarding decisions, and they can send it to the next router on the path until it gets to the destination. That's how the internet even works today. So there is a database always, and this database can be built statically or manually, or it can be using dynamic routing protocols. So basically enable a forwarding protocol here and a forwarding protocol here, and they will exchange the information in the sense of routing updates. On the internet, the most famous one is called Border Gateway Protocol, or BGP. This is the most famous one that has been used on the internet for decades right now, successfully without any issues. And we don't know anything about that. We are just using the internet and we have no clue what's going on under the hood, basically. Okay, so the internet is nothing more than a huge number of routers that are interconnected with high-speed connections. And a user sitting in the US could be talking to a web server in India, and it happens in a fraction of a second if we have good internet connection. Okay, and as we mentioned, there are devices that can do both. They can do routing and switching. And an example is the Wi-Fi router we have at home. Hopefully you found this crash course beneficial. As I mentioned earlier, we are working on a more detailed IT fundamentals. So the IP addressing part, the TCP IP, the routing and switching, and also there will be a lot of quizzes and assignments, and maybe also a design assignment at the end, or a capstone project where you are going to design a network with IP addressing, with the components that are required. And this is going to help you avoid wasting time and money on a lengthy A+, Network Plus, CCNA route if you are going to the modern IT careers. So if you are headed into network and you love network and you have passion to the networking, then go ahead and follow the old IT as you wish. But here I'm talking about preparing people to avoid wasting months and months and thousands of dollars on exams and on content that is not required, and on certificates that will not get you through the door into the modern IT jobs. So that is going to happen in the next couple of weeks, and I will share with you the news when that is ready. All right. So please don't forget, subscribe to the channel, activate notification to receive similar courses and similar videos. And also, if you benefited from the course, please consider giving us a like, share the video with others so the benefit is going to reach the masses. Thank you so much, and I will see you in the next video. Ciao.